Hello everyone, my name is Xiaogang Xu. I'm from the Chinese University of Hong Kong. Today I will present our paper, View-Independent Generative Adversarial Network for No-View Synthesis. Multiple view transformation means generate a novel view for a given 2D image. We think such transformation can be divided into two phases. First, obey view-independent representation, and then apply view-specific parameters onto this representation. To obey view-independent representation, some current method will first obey 3D reconstruction, and then render it into the target view. However, getting 3D models is difficult. There are also some methods that first obey features through encoder network which are irrelevant to different views, and then combine it with the target view label and send them through decoder to obey the final result. Such methods often adapt adversarial training by adding discriminators. However, they only deal with the situation where viewpoints are discrete. Our work aims to train learning-based models which can be applied into different tasks, including face and general objects, and our model is suitable for the situation where pose parameters are continuous. In our framework, we first send source image and its camera pose to an encoder to obey view-independent features. Then the target pose parameters are sent through the pose feature extractor to obey its deeper feature representation. They can be fused and then passed through the decoder to obey the final result. To train the overall framework, we set several laws here. The first one is the image reconstruction loss, which mentions the difference between the generated output and the ground truth. We also set a cycle consistency in our framework, since we have obeyed the final output and we can generate the source view again by such paths. The difference between this cycle output and the source image can be set as cycle consistency loss. As we have stated, we need to ensure the obeyed features having view-independent property. This can be done by pushing those two features in cycle paths to approach each other. Adversarial loss is set here to enhance the quality of final output. This is done by adding a discriminator and set the adversarial loss as the form of W-GAN GP. We also built a post discriminator to ensure the accurate pose of output. The discriminator tries to regress the pose parameters of real images, and the generator, on the other hand, tries to push the discriminator to output the target pose for the generated images. As our motivation, our framework can be applied into many tasks once there is pose information in the corresponding dataset. The first task is the face restoration with several fixed viewpoints. Given the original images and the target viewpoint label, our framework can generate the target view with accurate texture and pose. We compete with two GAN-based approaches, which also can do the task of face rotation and provide some quantitative results. We can see our method has higher. The first task is the face rotation with several fixed viewpoints. Our method can also deal with a situation where camera pose parameters are continuous, once the users give the target pose parameters. We show several examples here. There are examples will turn face to left. Those are examples will turn face to right. Compared with face rotation, the rotation of general objects is more difficult, and our method can also obey good performance on such tasks. The following is the result where the data comes from the category of chair, sofa, and bench. Meanwhile, we compare our method with two approaches for those three categories and found our method has better performance. That's all, thank you.